Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In the lecture series of Material Studio, we are at the lecture number 37. And in today's lecture, we will learn how to calculate phonon density of state and phonon dispersion and CASTEP. So basically, these properties help us understand how atoms vibrate in a solid and whether the structure is dynamically stable or not. And vibrational study are important when we are working with materials used in electronic, thermoelectric, catalysis, and even battery applications. So now in this lecture, I will first discuss the Phonon result that I have already calculated for the material SRTIO3, and after that I will walk you through the practical steps using CASTEP and Material Studio, including how to properly set up the and run both Phonon DAS and dispersion calculation. So let's begin with a bit of backgrounds. In a crystal, atoms are constantly vibrating even at absolute zero, and these vibrations are quantized into particles called phonon, similar to how light in quantized into photons. So phonon carry heat, effect and affect thermal conductivity, and also influence structure and electronic properties. Now, a phonon dispersion is a graph that show how phonon frequency vary with respect to wave vector along different direction in the Brillouin zone. And phonon does tell us how many vibrational mode exist at each frequency level. So let's take a look at the results I obtained for SRTIO3. First, let's understand the phonon dispersion curve. You see on the x-axis, you will see several high symmetry point in the Brillouin zone, like gamma, f, q, z, and back to gamma. So these represents a different direction in reciprocal space. The y-axis represent the phonon frequency and terahertz. Each line on the graph represents a vibrational mode at the gamma points. The three modes start from zero frequency. You see these three are start from zero frequency. These are the acoustic phonon branches which are always present in solids. So the rest of the modes are optical phonon which vibrate with higher frequency. And the most important thing is note here is that all the frequencies are positive. There are no imaginary frequencies which would have appeared below the axis. So what does it mean? This tells us that the structure of SRTIO3 is dynamically stable and the configuration are used. If any modes had imaginary or negative frequency, it would indicate structure instability or improper relaxation. Now moving ahead towards the phonon density of state. In this graph, the x-axis is again phonon frequency in terahertz, and the y-axis show the number of vibrational modes per unit frequency. So you will notice that there are clear peaks in different frequencies range. The low frequency range from around 0 to 6 terahertz mostly come from vibration of the heavier atom like ST and TI, and the high frequency region especially from 20 to 24 terahertz is due to the lighter oxygen atom which vibrate more rapidly due to their lower mass. So these pattern gives us a deep insight into the internal vibration and how different atoms contribute to heat and lattice motion. Now that we have discussed the results. Let me walk you through how we perform this calculation, how to set each parameter for the phonon calculation in CASTEP. So I begin by optimizing the geometry of the set structure to ensure the structure was properly relaxed before starting the phonon calculation. And the setup, I use GGA with PBE exchange correlation. Regarding the logarithm, I use BFGS. Yeah, I use BFGS which efficiently minimize energy and force. The energy convergence was set to 1.0 electron 1.0 e to the power minus 5 electron volt per atom, and the maximum force was set to 0.003 electron volt per angstrom. The maximum stress was 0.05, and the maximum displacement allowed during relaxation was 0.001. So the most important thing is that I use non-conserving pseudo potential, which are preferred for you see regarding the yeah, I'm sorry. Yes. So the most important thing is that I use non-conserving pseudo potential, which are preferred for Phonon calculation. For Phonon calculation, yes. So for k point sampling, I use 2 by 2 grid. Here it show 1 cross 1 cross 1 because the calculation is already done. So once sometime the parameter has been disturbed once the calculation has been completed. So 2 by 2 grade which is acceptable for this type of material and calculation. And once the structure here just a second. So once the structure was optimized, I switch the CASTEP task. I switch the task to properties, and from property section I choose the and from the properties tab I choose the phonon. You see here I choose phonon. I enable both Phonon DAS and Phonon Dispersion. Since we know SRTiO3 is a polar material, so I also check the box to include LOTO splitting, which account for the difference between longitudinal and transverse optical modes due to polarization effects. And in the method tab, we have a two method to calculate Phonon DAS and dispersion. The one is linear response and the second one is finite displacement. So I choose linear response method, which is based on density function perturbation theory, and it provide accurate result, especially for polar material. And I set atomic displacement separation is 0.015 astron, and also the G vector range from 0.05 to 1 angstrom. This will you define how the system will be perturbed during the Phonon calculation. So after that I submit the job and calculate Phonon DAS and Phonon dispersion. So this is where I access both the Phonon dispersion and DAS, which I already show you the graph and I discuss. So I found the result were clear, and the data confirmed that SRTiO3 is dynamically stable and well behaved. So to summarize the lecture, Phonon dispersion and DAS calculation are essential to check the stability and thermal behavior of material. And in this lecture, we understood what these concepts mean, looked at real result for SRTiO3, and then learn how to set up the entire calculation process using CASTEP and Material Studio. So if anyone have any question regarding the calculation steps or regarding the these graph, so let me know in comment. I will respond to you. And with this, thank you very much. So if you found this video helpful, please make sure to like, subscribe and share it with your fellow student and researcher. And if you want me to make more videos on the like on this topic, like how to calculate thermal conductivity or any thermal properties from Phonon DAS, do let me know in the comment. I will make a video. And once again, thanks for watching, and until next time, Allah Hafiz.